All right, everybody. So today we are going to be reviewing bivariate data, which is what we covered in Unit 3. So remember, bivariate data is where we're comparing the relationship between two different variables, x and y. So the way that, remember that we graph that is by putting it on a scatter plot where we can easily see the relationship between x and y. The way that we're going to describe it is using our acronym FORWARDS to make sure that we include all these different components. So the form is going to be talking about whether it's what form does the points from the scatter plot take. So you have a lot of different options in real life. On the AP test, they're just going to be testing really linear or non-linear. So if it looks like a straight line, you say linear. If it doesn't look like a straight line, you say non-linear. You could also do quadratic forms, exponential forms, any type of function. But just for the AP test, we're going to be dealing with linear, nonlinear, because that is what you will see most often in real life situations. Remember, the O stands for outliers. So if we just see anything that looks like a possible outlier, we will make note of that. R is our correlation coefficient, which helps us determine our direction and strength. Direction is going to be positive or negative. Positive if the trend of the scatter plot points is going up. Then it's going to be negative if it looks like the trend of those points is going down. The strength is going to be anywhere from very strong to very weak, and then there's kind of like a sliding scale in between there. If the points are really close together, then it's probably going to be a strong relationship. If it looks like a very straight, strong, close to being a very straight line, it's going to be a strong relationship. The points look more scattered randomly, it's going to make it weaker. So perfectly strong graph would be all the points going straight up in a line, something like this, or down similarly. And then if we had a weak correlation, then they would look really randomized. So going into that, you really have to make sure you understand what the correlation coefficient is, which remember is abbreviated by the lowercase r. Correlation coefficient is going to be on a scale from -1 to +1, where -1 is strong and negative, and then 1 is the most strong you can get and positive. Then you have that sliding scale in between, where 0 is going to be the weakest possible correlation that you could have. So you're going to most likely 99.9% of the time have a correlation coefficient that's somewhere in between those three numbers. So you kind of have to use your own discretion, determine whether it's strong, moderately strong, positive, negative. That's really straightforward. If it's a positive number, if R is positive, it's going to be positive. It means the graph's going to be going up. If it's a negative correlation coefficient, the graph's going to be going down. It's a negative correlation. But the strength, there's not like a set yes or no for that. So generally, if you have like 0.5, you might say that's moderately strong. And then the closer you got to 1, you'd probably transition into strong. If it's less than 0.3, you're probably going to say it's a weak correlation. Now, let's go on to this next part here, where we're dealing with the regression line. So this is what a regression line looks like. Remember, when we're graphing a regression line, this is a line of prediction. So way to predict operating or predict y values for x values we haven't collected yet. The example that we did in class was where we were dealing with the balloon activity, where we're seeing how the length of the balloon related to how long it would fly in the air. So we used our regression line to predict how long a balloon would fly for lengths that we did not actually go through and collect in class. So that is what a linear regression line looks like. Another way of saying it is a line of prediction. And based off our computer output table, which they'll give you on the AP test, that is going to be giving you the equation for this line. So let me zoom up here so I have some room to write. All right, here we go. So I know there's a lot of numbers on this, but the ones that I drew arrows to, those are the ones that you need to know. So this number on the bottom, so that first column, bottom number, that's going to be your slope for your regression line. So if I'm writing out my regression line, remember we put that hat over the y because that's like notation for prediction. We have 14.673, and then that's our slope, so we put x after it, plus our y-intercept, which is going to be plus, I'm going to write this down here since I'm running out of room, plus 1136. So the 14.6 is our slope, and then the number above that on the chart, the computer output table, 1136, that is going to be your y-intercept. And then we can use this to predict values by just plugging in the value we want to predict for x, and that gives us our prediction for y. All these numbers right here, we're not going to deal with those. You don't need to worry about those. We'll deal with some of them next week when we learn a couple new things dealing with this, but for right now, don't worry about it. And then, same thing with this f and the r-squared adjusted. Really important that you do not put r-squared adjusted when asked for r-squared on a test. Then we have r-squared. So the regular r-squared is going to be the one that we want to use. So first thing, we can find r from r-squared just by writing out a little equation. So we get r-squared equals 57% as a decimal, so we put it as 0.57. We take the square root of both sides, and that gives us r equals I can make a decimal point, there we go, 0.75. So basically, if we go off that scale that we just went through and reviewed, that would probably put us in positive and probably the strong correlation, since we're getting pretty close to that end of the scale at +1. Now we also have our r-squared value, which we need to know how to interpret. And basically just understand, memorize this sentence, and then if it comes up on the test, you just plug in the values. This isn't a concept you really need to understand conceptually super in depth. So the main concept is r-squared is telling us what percent of the variation in our data is explained by the regression line. So the sentence you want to make sure you memorize is about blank percent of the variation in your y variable is accounted for by the regression line relating the y variable to the x variable. So I know that's a lot of words. Let me do it in context with this problem. So about 57.0% of the variation in operating costs per hour is accounted for by the regression line relating operating costs per hour to number of passengers' seats. Okay, so that's it. Just want to make sure you memorize that interpretation. Next, we got our residual, which, remember, the way we calculate residual is you take your actual value. Forgot the T on that. Let me write that in there. So actual value minus your predicted value, which gives you residual. Your actual value is going to be a point that you actually observed during your study. So you could see that as a point from your scatter plot, an ordered pair that's given to you in the problem, or a point from like a table with x and y values. This one that we just went through and looked at. So any of these points would be actual observed values because they're points. Now, if we looked at the predicted value, we can get that by plugging in an x value into your regression equation, and then y is going to be your predicted value. Or if you could kind of estimate it looking off what your graph is. So let's go up here. And let's say I wanted to find a predicted value for a 350 passenger seat plane. So I go there on my graph and then see where it comes out to on the y-axis, which is about $6,250 for your operating cost. Okay, so you can estimate it based off the graph. To find the exact value, I want to plug in that 350 in for x. So I'll do that on my calculator real fast. Putting in those numbers times 350 plus 1136. So the exact value would be 6,271. So if you want the exact value, you want to make sure you plug that x value in for x in your regression equation. So then to get a residual, you just subtract those two different values, what your actual value is minus your predicted value. On the graph, that's going to be the vertical distance between a point and the regression line. So let me zoom in so I can show this to you and erase all this other stuff. All right, so I'm going to zoom in so you can see the graph nice and easily here. So the regression is going to be your actual value minus your predicted value. So in this case, if your actual value is going to be below the line, that means you have a negative residual value. In this case, if it's your actual points above the regression line, that's going to be a positive residual value. Also, before we go on to slope and y-intercept interpretation, remember you can also have a residual plot which plots your residuals, and if the residual plot looks like it's random, then we say a linear model is a good fit. If a residual plot looks like it forms some pattern, any type of pattern, most of the time it'll be a curve, then we say a linear model is not a good fit, which is kind of opposite of what it is for a scatter plot. So make sure you make that notation for a residual plot. If it's random, linear is a good fit. If it's not random, linear is not a good fit. All right, then slope and y-intercept interpretations. The way we interpret the slope is when x increases by 1, y increases by the amount of the slope. So you just plug in the values that you have for your y-intercept there, and want to make sure that you're also incorporating context. So let me do it for this example up here. So since our slope is 14.673, so I say that every time for every passenger, every seat that's added to the plane, because that's what x represents. So when x increases by 1, it means that we're adding a seat on the plane. We expect that the operating cost per hour is going to go up by $14.673. So $14.67. So that's how we interpret the slope. And then for the y-intercept, a lot of times this probably won't make sense, just given the context of the problem. But the way that we interpret that is when x equals 0, y equals the amount of the y-intercept. Like I said on there, it doesn't always make sense. Like this example where it's not going to make a lot of sense. So if x was 0, that means when there was no seats on the plane, we expect the average operating cost per hour to be $1,136. So $1,136, which doesn't make sense because you need to have a seat on the plane, right? You're never going to have a plane without any seats on it. So that's when it a case where it would not make an example, but there are certain cases where it would make sense. So then you would have to know how to interpret it. So I know that was a lot, but that's just a quick kind of crash course reviewing all that stuff that we did from Unit 3 all the way back from the end of September. So make sure that you kind of understand all this before you get started with the free response questions today and next class.